it's going around the curve. All right, as the person goes around the curve, and say they're making a left-hand turn, going on a left-hand curve here, what force is actually pushing it? We know that there has to be a force, right? There's got to be a quote-unquote string in every situation, right? The string that held the stopper and kept it from going off in a straight line has got to be pulling to the inside for it to go around a circle. What causes the car to pull to the inside? Well, the only thing that you got is, no, you usually don't put the brakes on to turn a car, right?
Acceleration.
You turn the wheel and it's the tires and the road, right? And what's the force between those two surfaces called? Friction, right? So it's actually friction that causes the car to turn. And we can kind of intuitively appreciate that. If a car doesn't have good tires, the tires are bald, you're not going to have as much friction, and you're going to tend to slide when you go into a curve, right? Friction is going to actually be pulled to the inside. All right, so our F is to the inside. What are the other two forces?
Gravity.
All right, force due to gravity. mg is going to be going down.
And then normal force.
And a normal force, because you are on the surface this time, n. All right, and then we want to drive to an equation. Kind of fun there. Our friction is equal to mv squared over r. All right, there's our equation. All right, we can even extend that equation and say frictional force is equal to mu n, isn't it? And in fact, in this problem, what's n equal to? mg. So mu is going to equal n, mu times mg, that's what the normal force is equal to, equals mv squared over r. What happens to the m's? They cancel out. Mu is equal to v squared over rg. All right, so I'll give you a chance to copy that down, and I'm going to erase this friction equation, and I'm going to put actually mu equals v squared over rg, if you guys all remember how we got that. All right, we originally said the force that produced the circular motion is friction, and that's got to be equal to the centripetal force, mv squared over r. And if we go through that and figure out, we could actually come up with an equation for the coefficient of friction. All right, we got that copied down? All right, we're going to put in mu equals v squared over rg. All right. All right, third example. Car on a banked curve. And I'm going to add into the banked curve that it's frictionless. In other words, we just had friction last time. What if you were on a frozen highway and there was some sleet on top of it and it was almost like a coefficient of 0 going around the curve? How could you get around that curve? Well, if the curve is banked, what do we mean by a banked curve? Right, it's sloped towards the inside of the curve. You might see it in maybe some race tracks, right? As race car drivers go around a curve, there's always a banked curve. And we see it on our highways. The highway banking is not nearly anything like Indianapolis 500, but there is still a bank to make it easier to navigate a turn, right, on a slick highway. And what we have is a banking that might be something like this, and there's an angle of banking as you're looking from behind on a car. As the car is rounding a curve, and if there was no friction that was actually driving this car around, I'll put the tires underneath that actually car. If there's no friction between the tires and the road, if you're banked, the curve is banked right and you're going at the right speed, you can take your hands off the wheel and the banking will allow you to go around that curve. All right, let's take a look at the free body diagram. Well, first of all, what force, I'll leave this a mystery for a second. Let me start with a big free body diagram. What are the forces involved if there's no friction? All right, the normal force by the road, and what direction is that pointing? All right, it is perpendicular to the surface, right? So it's going to look like this. Normal force is in that direction. Actually, probably the angle's a little bit more than that. And what's the other force? And what direction is that pointing? Straight down. And if I broke N into its two components, N, Mg, broke N into its two components, the component that's going up, here's this angle. We could take the time to explain that this is this angle of banking is the same as this angle here. We could go through and do geometry here. I guess this angle here is the complement of that angle. All right, so we could write that 90 minus theta for that angle. That's the complement of this angle because it's a right triangle here. You have a vertical angle over here, which makes that equal to that complement. And now that angle is complementary to this angle, isn't it? All right, so that makes this theta. All right, so that theta, the theta of the banking is the same as the theta, how far the normal force is away from vertical. All right, so this component is going to be what? It's the adjacent side next to the angle. N times cosine of the angle. What's this side going to be?
Sorry.
N times the sine. All right, now, what's the force that causes it to go around the curve now? All right, what is the string that's pulling it to the inside? What force is pulling to the inside? It's a centripetal, that's what it's going to be equal to, the mv squared over r. But what physical force is actually producing? What's the string? What's pushing it to the inside?
Gas.
It's going to be this component, isn't it? Isn't that going towards the center of the circle, the n side? All right, so in this case, it's the normal force that causes you to go around the curve. It's actually a component of the normal force. The one just opposes the weight, the n cosine. It's the n sine that's actually pulling the car to the center of the circle. So we can adjust our free body diagram to have n sine going to the inside and n cosine going up. All right, now we get to our equation. Instead of me writing the beginning point in here, I want to write a final equation. I'm going to say the force that produces the centripetal force this time, the first time was tension, second time we had friction, this time what is it? It's the n sine. That component is actually what's producing the circular motion. What's that going to be equal to?
mv squared.
mv squared over r. That's my first equation. We can put that in here, but I want to go a little bit farther. N cosine is equal to mg, isn't it?
Yeah.
So that means that n is equal to what? mg over cosine. If I substitute n in that equation, what n is equal to, into that equation, I get mg over cosine times the sine equals mv squared over r. What happens to the m's?
Cancel out.
You notice how many times in all these equations the m's cancel out. They don't write a speed limit for a curve depending on the weight of your car. It doesn't. That's not a factor. It's how much traction you have in your tires. What's the sine over the cosine equal to? Or pre-calculus tangent, right? So G tangent, our equation is simple as we see, is V squared over R, and tangent is equal to V squared over RG. All right, that's the equation I want to put in there. The tangent of the banking angle is going to equal V squared over RG.